Another theorem in section 7-5, and I have it on display here, but it would be in notes that you've received, is theorem 7.11, the triangle angle bisector theorem. Now, in this particular theorem, we don't have similar triangles, even though it's in the section regarding parts of similar triangles. But what this involves is the bisector of an angle in just a single triangle. And what the theorem states is that if a segment is the bisector of an angle of a triangle, then it separates the opposite side into two segments that are proportional to the lengths of the other two sides. I want to break that down a little bit. So here we have segment KM that bisects angle LKJ. So what that segment does is it divides this side into two pieces. The distance from J to M and the distance from L to M. And those two are in proportion to these two sides. Now, how we can kind of think about that is if I just separate it to the two sides of the bisector. So JM corresponds to JK in the same way that LM corresponds to LK. And so that's our proportion. Notice these are to the left of my angle bisector. Segment JM is on the side intersected by the angle bisector. And these two segment distances are on the other side of the angle bisector. Now it's important to remember, the angle bisector does not always, in fact most of the time, does not intersect the opposite side of the midpoint. It's really tempting to say, oh, then M is the midpoint. That only works if we're bisecting the vertex angle of an isosceles triangle. I don't know that these two segments are congruent. So I cannot say that M is the midpoint here. All right, let's look at a couple of examples of how I would apply that. So in this particular case, I'm trying to find the value of x. Notice that this segment is the bisector of this angle of our triangle. So if I look to the one side of the angle bisector, the ratio of these two distances would be the same as the ratio of these two distances. I just have to make sure I put them in the proportion in the right way. Now, if I can at all possible put my variable in the numerator, that's what I want to do. So in my proportion, I can say that x corresponds to 15 inches in the same way that 20 inches corresponds to 24 inches. So notice this was the side opposite the bisected angle. These two distances are the parts of that side. These two distances are the other two sides of the triangle. Now, can I make my proportion a little bit easier to work with? Yeah. 20 inches and 24 inches are both divisible by 4 inches. So 20 inches divided by 4 inches would be 5. 24 inches divided by 4 inches would be 6. Horizontally, 6 and 15 can both be divided by 3. Now, I could do cross products here, but essentially, since x is already in the numerator, if I just multiply both sides by 5 inches, my variable will be alone. So I'd have x on this side. 5 times 5 inches would be 25 inches. And then we have 2 in the denominator. Now, most of the time, I don't express inches as improper fractions. I'd probably want to do that as a mixed number. So 2 divides into 2 once. There aren't any left over. 2 divides into 5 twice, but since 2 times 2 is 4, there's 1 left over. So the 1 that's left over still needs to be divided by 2. And so x would be 12.5 inches. Now, if you used your calculator and divided that and got 12.5 inches as a decimal, that's okay. Now, I also want to look at an example of that theorem that might be considered a little bit more complex, a little bit more difficult. So in this example, we want to find the value of W. So notice W is this distance. We do have the angle bisector of this triangle intersecting this side. So we know that the ratio of W to 9 centimeters equals the ratio of this distance to 28 centimeters. The problem is we don't have that distance identified. We know that this entire segment's 30 centimeters, but we need to write an expression for this piece. Well, let's suppose this were 10 centimeters. This would be 20. How would we know that? Well, 30 minus 10 is 20. Well, I'm going to do the same thing. I'm going to take the total distance, subtract this distance, and that's going to be the length of this segment. I put that in parentheses because all of that is in centimeters. So now I know that W compares to 9 centimeters in the same way that 30 minus W centimeters compares to 28 centimeters. Now, in terms of reducing here, I know it would be awfully tempting to say 2 divides into both 30 and 28, but 30 isn't the number here. 30 minus W is, and the 28 doesn't divide into the W part. I could reduce the label of centimeters, however. 9 doesn't share a common factor with 28, so I can't reduce horizontally there either. So now, what I'm going to do, if I look at this one, since I have the W's on the both sides, I am going to do the cross products in this case. Because if I multiply by 9 centimeters, I still have a W on this side. So doing this cross product, 28 times W, on this cross product, I'm going to have 9 centimeters times 30 minus W. I'm just going to put the centimeter label part at the end. So now we'd want to distribute. So we'd have 28W equals 9 times 30 is 270. 9 times a minus W is a minus 9W. And we know this is in centimeters. So now I could add 9W to both sides. So 28W plus 9W would be 37W. And here we would have 270 centimeters. So we'd want to divide both sides by 37. Now, again, remember the metric system uses decimals for its measurements. So what I'd want to do is actually perform a division there. And so if I get my calculator out, and take 270 divided by 37, divided by 37. Notice it gives me that decimal. I can see that 297, 297 keeps repeating. So I do want the exact value here. So W is equal to 7.297 repeating centimeters. Depending upon the problem itself, it might ask you to round to the nearest tenth of a centimeter. So in that case, we'd say that W is approximately 7 point. Now we have to see, is it closer to 2/10 or 3/10? If we look at the next digit, anything 5 or greater, we would round up to the next tenth. So this W would be approximately 7 3/10 centimeters. So those two examples show how we can apply the triangle angle bisector theorem.